All right, here's a question that talks about the molar volume of a gas at a high pressure. 10 megapascal happens to be much smaller, 0.011 times the molar volume at a lower pressure, 100 kilopascal. Also sounds like a large number, but this is approximately equal to 1 atmospheric pressure at the same temperature. Okay. Now, it also says that the intermolecular forces of attraction are negligible. We need to find out the volume of the individual gas molecule. Now, the fact that it's talking about the volume of the individual gas molecule, that means that we're talking about van der Waals equation of state, which is this expression right here. Now, the reason why I said this is because the ideal gas law assumes that, well, the gas molecules don't have any volume. If you're talking about the volume of a gas, this is the equation we need to use right here. It also says that the intermolecular force of attraction is zero. If you remember the theory, you'll know right away that this means that A is equal to zero, which means that this entire term gets cancelled out. If you don't remember that, that's okay. There's another way to get around it. The deal is, if you remember this graph, the theory, when you plot Z versus P, this line here is Z equals 1, you have many gases, right? This is hydrogen, which has no intermolecular forces of attraction, okay, which is similar to this. And then there are other gases that have a bit of a dip. And the larger the dip, the greater the intermolecular forces of attraction, okay, which is this here. If you like math, you will appreciate this right away, that the first one, yeah, the top one, hydrogen over here, it has the form of y equals mx plus c. This is a linear equation. And all of these, there's some polynomial factor involved, which is why there's a dip and there's a curve, there's a strange curve. This polynomial bit, the intermolecular force, is this term right here. And the straight line, y equals mx plus c, would be only because of if you ignore a, which is this right here. So this is another way of internalizing the same idea of what you mean by the intermolecular force of attraction. And sometimes students get confused between A and B. This is how I remember it, okay? That A has to do with the intermolecular forces. So write that at IF, and B is the volume of the actual gas, which is what we are concerned with right now. Now, B is a representation of that volume. It's not equal to that volume. Yeah. First of all, this B, whatever value you get, the units of B are going to be liter per mole or meter cube per mole. That's the unit that you have. Okay, I'm going to put that in curly braces. Now, we are talking about individual gas molecules, which means that the value that you get will have to be divided by Na first. Yeah, the what is the representation? And most importantly, this is equal to 4 times the volume of the actual molecule. This is the excluded space. Okay, now excluded space talks about, there's a bit of a derivation. I'm not going to get into it, but basically, if you have two hard spheres representing the volume of the gas molecules, when they touch each other, nothing else, no other molecule can occupy that space. Hence, this is the excluded space. After the derivation, you get that is equal to 4 times the V of volume of the actual molecule, provided you divide this by Na, yeah, to get rid of this mole business. Okay, then you're talking about individual gas molecule volume. All right, so that was a condensed version of what we are going to do in this entire question. Let's get started and do this in a bit of detail. So yeah, just writing down the things that we got from the question. The initial pressure is this value. The initial volume is smaller than this final volume, and the final volume is here, V2 itself. Final pressure is lower. Sometimes students can mix up these two. That would be criminal. But hey, the easy way to remember this is PV is equal to constant, right? Because the temperature is constant, right? So if P increases, V falls. So this is a quick way of checking what you're doing throughout. We've said that A is 0, and we need to find the volume of the gas molecule. From the van der Waals equation that we wrote down, we said that this term is 0 because A is 0. And now you have 3 equations and 3 variables. Okay, what are these 3 equations and 3 variables? The first 2 come from the van der Waals equation, yeah, on eliminating the A factor. So this is similar to y equals mx plus c, where y is same as Z, which is PV by RT. Try this out. Yeah, if you don't take my word for it, try this out, you'll get this same form of equation. And the third equation is the relationship between the two volumes. From here on is just simple substitution. All right. And after you get this value B, then B by Na would be equal to 4 times the volume of the actual molecule. So V of the actual molecule would be this term right here. All right. B is the excluded volume. So let's go ahead and put actual numbers into this. I leave the substitution to the end. You'll see why. Let's write everything in terms of equations, and we'll do the substitution in the end. So we can eliminate B initially, and then substitute for V1 and get this V2. That's what we are doing over here. Okay, so here we have eliminated B from 4 and 5 to get this equation right here. And then we've said that V1 is equal to this 0.011 times V2. These values I already know, and temperature also is known to me, yeah, which is 300 Kelvin. This is why I've done these steps. Now, I get V2. I get the value of V2 from here, leaving everything inside here. I can choose to do this, or I can leave it like this, yeah, because all of this is a constant. Yeah, this happens to be, this is basically R. Yeah, I've done a bit of an approximation. I've taken R to be 25 by 3 joule per mole Kelvin, which is similar to the 8.314 number. It's an easy approximation to take. If you're working with liter atmosphere per mole Kelvin, then also you can use a similar approximation, which is 1 by 12, which is very close to 0.0821. I like doing this. It makes life easy. So yeah, you can choose to do this, put the numbers and get this, or just leave it in this. I'll tell you why we did that. Now, to get B, I can choose to leave these numbers out here, the constant that I had, and I get this term here. Yeah, it's a large number larger than 1, minus 1 happens to be multiplied with this, you get B to be this. Seems like a small number, but the actual volume is much smaller, obviously, right? I've taken an approximation of Na, Avogadro's number, to be 6 into 10 power 23. Remember, I'm dividing this because this is per mole. I need to talk about a single molecule. And then again, this is 4 times the volume of the actual molecule, and the answer that I get is this right here when I divide this number by 4, which is what we have done here. Cool, that's the answer. A quick recap of what we did. We started off with what was written in the question. We needed to internalize what's really happening. Yeah, intermolecular force is negligible, which means that A is equal to 0, which is what we did on this page here. We get this equation, one equation here, and a relationship between V1 and V2. You have 2 states, so you set up these 3 equations, and then we substitute for, we find the value of B, and B is a representation of the volume of the molecule. The actual value is B by Na is 4 times volume of molecule. Then we find the volume of the actual molecule, which is the answer that you see on your screen right here.